However, there's plenty of environmental exposure to carbon monoxide, so myoglobin needs to discriminate against it. Why? Well, carbon monoxide bound to the heme will inhibit its other duties, right? So storing oxygen in the case of myoglobin, or transporting oxygen in the case of hemoglobin, and it has other effects as well. There are heme proteins scattered throughout metabolism, and you can imagine that you would interfere with the function of those molecules as well, particularly energy metabolism. That's beyond our scope today. Let's just say that carbon monoxide actually has a higher affinity for myoglobin, or for myoglobin and hemoglobin, than does oxygen. So myoglobin has to discriminate somehow. In fact, the affinity for oxygen the affinity for carbon monoxide of free heme is something like 20,000-fold higher than that of oxygen. So if you had a free heme in solution out of the context of the protein, it would bind carbon monoxide much more tightly than it would bind oxygen. So how does the protein do that? Well, those interactions that I just told you about, the hydrogen bond that's going on here, and this strong interaction with the iron that's going on here, serve two functions. One is to increase the oxygen affinity, right? So there's a tenfold increase in the affinity of the oxygen relative to free heme, again, because of the presence of this distal histidine, and also the failure of carbon monoxide to form similar interactions with the histidine, because it's placed improperly, results in a 100-fold decrease in carbon monoxide affinity. So overall, you've improved the selectivity for oxygen dramatically just by placing this histidine here. Remember that carbon monoxide should be more or less vertical. Now, let me interject something that'll confuse you here. There's a lot of discussion in the literature about whether the carbon monoxide bond is distorted or not. But you can imagine that if there's a vertical orientation of that carbon monoxide, then lone pairs aren't going to line up appropriately to bind there. So in effect, even though, carbon monoxide still has a stronger affinity, this distal histidine serves to improve that affinity, or of the affinity for oxygen, many fold. I should also point out that another way that we overcome that high affinity for carbon monoxide is to make sure that carbon monoxide concentrations stay relatively low. So in the blood of a non-smoker, carbon monoxide concentrations are anywhere between 0 and 10 parts per million, whereas at sea level, I think the blood oxygen concentration is something like 2,000 parts per million. So there's a couple hundred-fold difference in the relative concentration of those two gases in any case. On top of that, you have this histidine-induced alterations in the relative affinities of those two. So tailor-made. Who's the tailor? Whoa, natural selection, of course. Okay, models, right. So let's concentrate on the bottom right here. This is a model of the fractional saturation. So I like to use these Greek letters. Oh, everybody likes to use them. So there's theta representing the fractional saturation of myoglobin as a function of ligand concentration. So makes sense. High ligand concentration, high saturation. So we see a binding curve here, and that looks like a rectangular hyperbola. So we want to start with a simple model. I love those simple models. They allow us to derive a mathematical expression that lets us quantify observations. So binding model for myoglobin, protein plus ligand in equilibrium with a bound state, so free to bound. We can write a dissociation constant for that. We could also write an association constant for that, but it's more convenient in most cases to think about dissociation, at least for us. So, right, the products of dissociation then are the free protein and ligand. The reactant then is the bound state, the protein plus ligand. Now, you can express a fraction bound here, and the trick is that we want to solve for PL. So this is a complicated expression. Let's simplify it so that we can express ourselves in terms of what we can measure easily in the laboratory, that is to say, ligand concentration. So if we solve for PL and rearrange, then we get this expression, which is a rectangular hyperbola. Beautiful, right? All we have to do is express things in terms of an equilibrium constant, and then as a fraction bound, and then we've got our graph back. And then we can make our measurements of saturation of myoglobin. Any number of ways you could do that. The easiest way you might do that, we're all aware, well, this is skipping ahead to hemoglobin, but the same holds true for myoglobin. We're all aware of the color changes that take place in these blood pigments as a result of oxygenation. Bright red for oxygenated blood, brownish maybe, or purplish if we're deoxygenated. A great way to figure that out for yourself is to cut yourself before you go out on a hike, and you'll see that your blood is nice and dark. And then when you start running up that hill, cut yourself again. Now, I should say that you might want to do this accidentally by falling off your bicycle if you're on a mountain bike ride or something. We don't advocate self-mutilation in this class, but if you did, then you'd see that the hemoglobin after exercising is much brighter red because it's oxygenated. Back to our story, though. We can make our measurements of hemoglobin or myoglobin oxygenation, fractional oxygenation, by measuring the absorbance of the solution. Right? If you suspend your myoglobin in solution, measure the color using a spectrophotometer, then you could potentially use that as a metric of the fraction bound, and then you can alter that by changing the presence of the relative concentration of ligand. This rectangular hyperbola expression will let you do that, and what can you get out of it? A simple number that you like, the dissociation constant. So you can quantify the dissociation constant. Now you might say, well, Gillespie, you could just look at the data and sort of estimate what KD is. What's KD? Let's define it as the ligand concentration at 50% of saturation, so somewhere around here. You could just eyeball that, but we like to quantify things. More than that, we have a model that tells us that we understand the way myoglobin behaves in terms of a simple system. So we can extract a KD. Now, another reason for extracting a KD is that we can make comparisons between one system and another. We make a mutant in myoglobin, for example, or we present an alternative ligand, and then we can establish the differences in binding affinities of the protein for those different ligands or in those different backgrounds.